Okay, so we talked a while back about biasing. We talked about how we can make current sources and how the biasing is different in an integrated setup from a discrete setup. They are different. Why? What was the primary reason for the difference? Was primarily an economical and convenience reason, in the sense that transistors were cheaper, were very cheap in discrete, in an integrated setting, and discrete parts where like resistors and capacitors were a lot cheaper in a discrete setup compared to the transistors. And what that did, it basically made it possible, made it so that certain kind of design was preferred in one kind of setting compared to the other. Anyway, so one of the things that we did in integrated setup was these current sources. So we said, well, how do we make current sources? So we started with current sources, and we said, well, the basic building block of a lot of these things was the current mirror. So you can have MOSFET or bipolar current mirror, and what you had, this is the simplest current mirror. So you have some reference current here that could be mirrored here. In general, it could be actually multiplied or divided by some ratio. So if you could basically control the ratio of W over L of this guy, W over L of that guy. So if you could make this W1 and W2, you could make the ratios of the currents ratio of W1 and W2. And the main reason was that they shared the same VGS. So if you looked at the equation for the ID, was basically mu n Cox over 2, W over L, VGS minus VT squared. And if you solve for VGS, you see that VGS is VT plus square root of ID over mu n Cox over 2, W over L. Now, there was another parameter that we commonly refer to, which was delta VGS. Delta VGS was defined as the VGS minus VT. It's known as the gate overdrive. Because that's the, up until VT, at least based on a simplified model, you don't get any current. Transistors off. You have to make it to the VT first, and then whatever you have beyond VT is what gives you the current. So really, if you can rewrite this in a more convenient form of mu n Cox W over L, of course this would be mu P if it's a PFET, delta VGS, which is the gate overdrive squared. And if you write it that way, then this equation basically becomes delta VGS is square root of ID over mu n Cox over 2 W over L. So these are reviews of some of the things that we did before. So we started with current mirrors, and we saw things. Now, one of the things that we saw is that if you have a current mirror, of course, what was the output resistance for a current source? The output resistance was what mattered. It was an important parameter. What made a current source was a high output impedance. So the question was, well, what if you don't have enough high enough output impedance? So what was the output impedance of this thing looking down here? RO of this transistor, right? So RO, whatever, 2. And it was determined by the L of the transistor and the DXT, DVDS, and all those parameters, right? So it was basically, if you wanted to think about RO, was basically, what was it? It was L over ID, DXT, DVDS to the power of minus 1. So that was its RO for MOSFET. And for a bipolar, it was VA over IC. Right? If you were a bipolar, it would be a VA area voltage over IC of the transistor. So we saw that the output resistance was important, and then to increase the output resistance, what did we do? We said there are several tricks. One of them was to use some sort of a cascode structure. So we made, for instance, a cascode current source. So to get an increasing in the output resistance, we made it into a cascode. And this was an example of a cascode. So you basically had your reference current here. And this is one of those reference currents we haven't told you how to make exactly. There's no simple ways of making this, which was by resistors, but in general, this is what it looked like. So now if you had something like this, what was the output resistance in something like that? I want a first order answer.
Beta on the wall.
No, there's a beta.
Yeah. Oh, squared.
Oh, that's good. GM.
GM of which guy?
Second.
This which was what you had before. So this, looking down here, you see RO2, and here you increase RO2 by the intrinsic gain of the transistor. So this is A intrinsic. So you increase it substantially, potentially. If your intrinsic gain, this is the maximum gain you can get from a transistor anyway. So you increase the output resistance by a large factor, potentially, if you do this. So it seems like this is a really good thing. So why is it that you don't always do this? What is there must be a disadvantage. Most of the time, there's a trade-off involved, right? So what is the thing that you lose when you go from this to that? Headroom, basically, right? How low this voltage can go before it stops being a current source, or the output impedance starts dropping. Because if you think about it, this voltage can go high, as long as the transistor, you don't exceed the breakdown voltages of things of that sort. But when it goes low, below a certain point for a given VGS, this transistor leaves the pinch-off region and goes into the triode region. And once it goes into the triode region, the resistance increases, because if you think about the IV versus VBS of the transistor, it kind of looks like that. You want to be here. That's where you have a high impedance. This is the V over I. Right? So the shallower the slope, the higher the resistance. But now here you have a low resistance situation. So then this is not going to be a current source, and this current will not be mirrored version of that current. So this is basically how far it can go. And what is the lowest this voltage can go before it enters the triode region? When does it enter the triode region? If you think about the gate overdrive across here, so this voltage being VGS, you really can think about the VGS as VT plus delta VGS. By definition, right? VGS is delta VGS plus VT. So every time you have a VGS, you can write it as a VT, which is a fixed amount, plus a delta VGS, which is the gate overdrive. So for this voltage, how low can this voltage be? Or what is the voltage at which this transistor technically enters the triode region? Of course, it's a gradual transition, but we have a definition. It's the delta VGS, right? Because remember, the condition for being in pinch-off is that VGS minus VT is smaller than VDS. So once VDS becomes equal to that, which is simply delta VGS, then you enter the triode. So the lowest voltage this can be is delta VGS. So as long as this voltage is greater than delta VGS, then you are in triode, in pinch-off. And if it goes below, you're in triode. How about here? So this is basically how low you can go on this voltage. How close to this lowest potential you can get. But how about here? How low can you go there? Well, let's find out. What is this voltage? Let's write it as VT plus delta VGS, right? Let's assume they're all the same size. They're all the same W over M. What is this voltage? It's the same voltage, right? It's a wire. So what is this voltage? You go another VGS up. What is the VGS? It's a VT plus delta VGS, right? These two have the same current, and so do these current too. There's no gate current, right? So this voltage is 2 VT plus 2 delta VGS, correct? Everyone agrees? Because VGS is defined as delta VT plus delta VGS. So there's one VGS here and one VGS here to get there. Now, what is this voltage? This one, the source of the M4. You go a VGS down, so this becomes VT plus delta VGS. So if this voltage is VT plus delta VGS, what is the lowest voltage this can be before it enters the triode region? How much voltage you need across this one? What's the minimum voltage you need across the VDS to maintain this transistor in the pinch-off region? It's a delta VGS, right? So this, the lowest it can be is VT plus 2 delta VGS. Correct? In this configuration. Now, of course, each one of these transistors needs a minimum of delta VGS, right? But this seems to be a little bit wasteful because it has an extra VT that you really don't need. Each of these, there are 2 transistors here on top of each other, and each one of them really needs a delta VGS, right? If you want to push it to the limit. But now you have the 2 delta VGSs plus a VT. So this VT is a little bit wasteful. And so in principle, if I could fix these voltages to any voltage I wanted to, I could lower this voltage by a VT, if I could lower this voltage by VT, this VT is redundant because see, this transistor, if this voltage is VT plus delta VGS, this transistor is far from being entering the drive, right? It has a VT of margin, has too much margin. And that means that you are losing a lot of headroom here. So how do I do that? Well, ideally, if I had a battery, I would put the battery here, right? If I could put a battery here, what would you set the battery to? What value would you set this battery to get the right voltage drops, to make this be able to go down as far as 2 delta VGS? A VT, right? You're 1 VT too high. Here, and hence there, and hence there. This follows that, and this follows this, in terms of like a dip. So if I could make this a VT, then this would fix itself, because then this becomes basically delta VGS, and then this becomes 2 delta VGS. So I can get much better headroom. Well, unfortunately, I don't have something called an ideal battery that I can use inside the jet. So I have to emulate it. The question is, can I do this? Well, where do you get a VT? Well, gate source of a transistor, right? So what if I put a follower here between these two? So I can make a follower and put it in there. So, well, it's going to be a little tight. So I need a follower here. Let's say connected to VDD. And then from there, I want to go to the gate. So this is my battery. This is to emulate that battery of this guy. And this is the lower transistor. And of course, this needs to be biased with something, so I put another current source on my current mirror chain. So you can see this is a current source, basically, of created. And it goes like that. So let's see if this does solve the problem. So what was this voltage? This is VT plus a delta VGS. Right? It's a VGS above the ground. What is this voltage? 2 VT plus 2 delta VGS. Because I've gone up another VGS across here. Another gate source voltage. Now, what do I drop across here? A VT plus delta VGS. So this voltage becomes VT plus delta VGS. And therefore, that means that this voltage is what? If this transistor were on and biased properly, this voltage would become 0. Which is not good because it drives which transistor into triode? This one, right? So this is no good. This needs to be at least delta VGS. So for it to be at least delta VGS, it means that I want this to be delta VGS. Which means that this has to be what? VT plus 2 delta VGS. Right? And therefore this voltage has to be 2 VT plus 3 delta VGS for this to work. If I wanted to do it that way. Or I could make basically somehow, so to get that, basically it means that I have to get this voltage higher. Right? How do I get this voltage a delta VGS higher? What is delta VGS?
Oh, we can change the W.
Yeah, so I have a parameter I can play with. Because so far I'm assuming all of them have the same W over L's. They're all the same size. But I need to make a change to one of W over L. For instance, this one, right? If everything is W over L, this one has to be changed. First of all, tell me which way should I change it. Should I make it larger or smaller to get more delta VGS for a given current? Smaller, right? So smaller the W over L, the larger the delta VGS. So I want to basically double the gate overdrive of this for a given current, right? Because I want 2 delta VGS across. Because this is VT plus delta VGS, and I want this to be 2 VT plus 3 delta VGS, which means that the voltage across here, it has to be VT plus 2 normal gate overdrive. So the new gate overdrive should be twice as large as the previous gate overdrive. So to double this, what do you need to do to your W over L?
1/4.
Make it 1/4. So if I make this 1/4, do you agree that this voltage drop would be VT plus 2 delta VGS, the old delta VGS, twice the old delta? So I have making this a quarter, I've made the necessary gate overdrive at that current, I basically double the gate overdrive. Right? And then if I do that, then the rest works out, because this becomes 2 VT plus 3 delta VGS, there's a drop here, this becomes VT plus 2 delta VGS, there's a VT plus delta VGS drop, and then therefore this becomes basically the orange stuff will hold, the orange values. So you see the trick? This is actually a useful trick. So by playing with the W over L's, you can actually modify the state. And this way now, this voltage, I've designed it so that it goes to delta VGS, and this can go as low as 2 delta VGS. 1 delta VGS here, 1 delta VGS there. So you can see it's more optimal. It's closer. I mean, there's no wasteful place. There's no place where I've wasted some of my voltage. Okay? So this is actually an interesting concept in design, and we can use it in other places too. So, nonetheless, this is still a stage that the current of this stage is controlled by this reference. So then now let's go start talking about how can we make these references, and what can we do. So what's the purpose of these references? Why can't I simply use a resistor? What is the problem with that? Well, I can use a resistor, but it doesn't give me certain things. So for instance, if I put a resistor there, or even more simply, a resistor here, what determines my reference branch current? VDD, so basically I have a VDD minus this VGS divided by R. So if my supply changes, if my battery is initially charged and then eventually is charged as it's changing, so your amplifier will behave differently when you pick it up from the, if you have a portable device, it would behave differently in the beginning, or half an hour later it would behave differently, and every time it would not be doing the same thing. Also, then it depends on temperature, because the resistor depends on the temperature, the VGS depends on temperature, a lot of things depend on temperature. And also if there are variations, for instance, this depends on VT, right? The VGS is VT plus delta VGS. So if VT changes with process variations, when one run, they have a slightly different VT, because what controls VT is the implant charge in the channel. If that changes a little bit, then the device behavior changes. So everything, it will depend on everything. They call it PVT, process voltage temperature. It depends on all of them. So the question is, how can we make it better? And you will see it will be done in steps. And depending on how accurate you want to get something, how accurately you want to do it, or how independent of these parameters you want it, you have to put in more effort, more design, more complex designs and things like that. So there's always a trade-off. You can't make it perfectly independent. You can make it as good as you want. Well, up to a certain point, of course. But you can make it very, very accurate. I mean, if you want to make something, a voltage, for instance, that's very independent, pretty much independent of supply, you can make something that doesn't change that much, very, very small variations in terms of tens of ppms or something like that, per degree, or ppms per degree. And there are precision things that even go below that. But you may or may not need it for your design. If you are designing something that the battery is changing from, let's say, a range of 25%, then you can get away with something relatively simple. But if you're making a precision device that will be used to make some very accurate beacon somewhere, to do something special, then you need to do a lot more. Anyway, so let's start with this. So let's start with the supply. I want to make things less dependent on the supply, because this is clearly very dependent on the supply voltage. If the battery changes, so is there a voltage? Is there a parameter which is coming from some of the process properties and some of the physics of the device and all those things that maybe I can use? Is there a voltage somewhere that doesn't depend on the supply? VT, for instance. We can start with the threshold voltage. The threshold voltage of the device is something that doesn't have its dependence on the power supply. So we can start with that. So let's see let's say I wanted to make a reference that generates a current that's proportional to VT. How would I do it? So where do I get a VT? Gate source, right? So that's in engineering, you always start from the simplest solutions and then see why, if it doesn't work, and then you go and fix problems, right? So let's say, I have a maybe I can take this current out. You can see this doesn't work because basically if you just leave it like that, the transistor will be off. Because there's no gate current, this will be driven to ground. So I somehow have to bias this resistor, provide this current somehow. So where can I provide this current? Maybe a current mirror. So I can take this current and say, okay, I mirror it. So this is a PTAT current mirror. So what I have here is that at least the theory of this thing is that this current and that current will be forced to be equal by this current mirror. If you didn't have any channel length modulation, let's say your output resistance is already large, these two currents will become equal, at least in this perspective. And if these two currents are equal, then the theory is that ID is basically mu n C ox over 2, W over M, VGS minus VT. So I know VGS is VT plus delta VGS. And then if that's the case, then this VGS is the same as that VGS, right? This is the same voltage. Therefore, this current is VGS divided by this R. So I becomes VT, well, VGS divided by R, which is VT divided by R plus delta VGS over R. And if you re-expand it, this is the V threshold over R plus 1 over R square root of I over mu n C ox over 2 W over M. So this is at least the way we think it should work. But there's a little thing you need to check. Right? When you make something like this, it's always you're creating feedback, right? You have feedback in this network. So let's check the polarity of this feedback. If this node goes up, what happens to this node? From here to there, what do you have? You have a common source, so you have an inverting state. This node goes down. This node is the same as that node. That node goes down. What happens to this node? Goes up. So you have positive feedback, and if you have enough loop gain around this positive feedback loop, then this could, instead of doing what you want, it could latch, basically. One side goes to VDD and one side goes to ground. So basically this can go to VDD, go to ground, or the other way around. This can go to ground, this can go to VDD. Something like that. So that's no good. So we have to get around that problem. One way to get around that problem is by basically just breaking this loop effectively by introducing a transistor here. So you can do this. If you introduce a transistor here, there's very little current, there's a little signal from here to there. The gain from the drain to source is very small. It's a reverse gain of a common base, right? Or common gate. So there's not much signal traveling this way. The signal can travel this way, but not this way. But if it travels this way, then it can't go this way, because then it has reverse isolation of this guy. So something like this, as simple as that. And then we have formed another loop here. We have a loop here. We have to verify this polarity, the sign of that loop. So if this node goes up, this node goes down. This is the follower node. This node goes down, which means that the feedback is negative. Something as simple as that. But the basic equation that we've written doesn't change, because still you have this VGS across this R. And these two presumably guarantee that these two currents remain the same, which is basically what you need. Now, you see I have a current that's proportional to VT divided by resistance, the threshold, plus this other term. So this is the desired term, and this is the term that's like a parasite. So if I wanted to make this term very small, what could I do? Because this term is the term that depends on other things, right? It still doesn't depend on supply, but it depends on other parameter and I and all those things. So if I make it independent of that, my current will be determined really by just VT over R. So what would you do if you wanted to make this term as small as possible? You can increase the W over. So make this W over very large, for instance. Right? And this is not a problem because this is a biasing network. So you can do this quite a bit. You can increase this quite a bit as long as you don't have physical limitations, because this is not supposed to be very fast anyway. This is a biasing network, so there's no trade-off between the capacitance and all these things here. So you can make this large, you can make this small, so you can make this approximately VT over R. That's one way of doing this. Now, so we've created a source. Basically, the current in these branches are approximately proportional to VT. Now, if I were to use this to bias something, how do I do that? Well, I can create an extra branch, right? I can just take this, and this is my extra branch. Now I can do whatever I want with this. I can bias current this way. If I do currents that are sinking current sources, then I can make another branch here, a mirror here, and mirror it back. So you can sink current or you can source current. So if you need to sink current somewhere to bias some stage, you can do it that way. If you need to source current to bias some other stage, you can do it that way. Right? Does it make sense? So that's a very simple system. It's not perfect, but it's not. Now, there are other ways of achieving this, and we'll see how we can improve upon this a little bit. If you want to use, yes.
When you want, after you build this current, this voltage supply independent current, and then you want to mirror it, or in the mirroring part, you still have the effect of supply because the VDS of that PMOS transistor, it appears in there.
So you have the effect of supply even here. You don't even need to get there. The supply, if you don't ignore the the channel length modulation, the output resistance of the transistor, even if you change the supply, you see some effect here. You've just reduced that effect. If you want to reduce it further, how would you do it? Let's say let's say this doesn't give you enough dependent independence. So what he says is that look, if you change the supply because you have a VDS here that's varying, and that will change the current because your current versus voltage for a MOSFET doesn't look like that. It looks like that. And as you change this VDS, as you change the supply, the VDS changes, so you change your current a little bit. So it's some dependence. So I will have some dependence of VDS, of VCC or VDD. So I will have some dependence on the VDD. And he's right. Right? So what do we do if let's say that was too much? We have reduced that effect because the slope of this line is not very large. Particularly if you use a large enough L. That's another thing you can do. You can make the channel length of these guys larger so the output resistance becomes greater, and that means that you have less sensitive, you get less channel length modulation. Because if you make your channel long, the same fluctuation in the voltage results in a smaller fractional change in the total length of the channel, and therefore the percentage of the current change will be smaller. But let's say it's not sufficient. What do we do? Can you suggest a solution?
Can you do a Cascode?
Yeah, you can make this Cascode, for instance, right? You can say, all right, if that's not good enough for you, I'll do this. And you improve that dependency by a GMRO. So you can improve it. So as I said, it's not none of these work 100%. None of them are mathematically independent of everything. But the sensitivity to different parameters is reduced. And you can reduce it by the desired amount. To the point that you may not care. If you're down to ppm, for most applications you may not care. Okay? Yes?
Suppose you did a Cascode, when you're mirroring it, do you can still use a single PFET for mirroring at the top, right?
Oh yeah, you could do that. You don't need this, for instance. So this one. That gives you more headroom,
Right.
but a lower output resistance.
Right.
So depending on what you're going to be doing with this, you may or may not want to do that. Because if your output resistance, for instance, if you don't do it that way, if you just take this, then this current would be more different from that than it would have been if you had this device. But this can vary more. Now, in this case, I would prefer to have this Cascode because I know this voltage is a fixed rate. This is like a VGS above the ground. and if I have enough headroom from the ground to the VDD to carry this voltage drop, then this is better because this guarantees more uniformity in the current between this branch and that branch. But if I had a problem for some reason I didn't want to use it, I can just basically drop this. So yeah, that's how circuits are. It's like there are many different ways. Each one of them gives you some advantages and some disadvantages. Anyway, so we took this VT, that threshold reference source, and we can make copies of that. Fine. But there are other ways of making these things. So now a lot of times, one of the things that you want to generate is that, what if I wanted to say, look, I can make my VT out of a single diode-connected MOSFET. And I want to drop this across a resistor. So I have a resistor, I have this diode-connected MOSFET, W over L, and I want to basically just drop this voltage. So I'm looking for a magic block here that does the following. This magic block forces these two voltages to be equal to ground. V1 to ground is equal to V2 to ground. And it forces these two currents to be equal. It's some sort of a current mirror, but it's more than a regular current mirror because it also forces these two voltages to be equal. The regular current mirror doesn't do that. So I call this a floating mirror, a mirror that can float in terms of voltage. So it maintains the two currents equal, but also forces these two voltages to be equal. How can I make that? Yes?
Is R a fixed value? Or
R is a fixed, an arbitrary value.
How do you maintain a constant current, constant voltage on any value?
This is a two-port. This is not a one-port. That's a very good question. If I had told you that I make this box that takes a resistor or whatever element is attached to it, and it forces an arbitrary current and an arbitrary voltage across that, you should have told me to go back and review your Ohm's law, the basics of the, Kirchhoff's law, right? Because you cannot force one, you can't force two. You can say I determine the voltage, and then the impedance of this guy, whatever this is, determines the current. Or if I push the current, then it gives me what the voltage is. I can't force both. But this is different because this is like two-port. There are two elements to ground, so it's different. There are two things. This is not equivalent to that. This is equivalent to. And that's allowed. If you choose these two currents, whatever value you could choose for this resistor, and you can think about this as a resistor, a different resistor. I can put two different same voltage on them, right? And basically, resistor doesn't perfectly work actually because you have to have some nonlinearity, but you have to have something that allows them to cross. Right? So basically, if it's a nonlinear element like this one, this allows it basically to find a solution. And sometimes there's more than one solution. Because of nonlinearity. For instance, you're basically trying to cross two curves. One which is like this, the other one which may be like this. And you have two or multiple solutions in general in a nonlinear system. You will see how it works. So, in other words, it doesn't, by the way, when I say this, it doesn't mean that I tell it what I1 and I2 are. I don't have a choice of what I1 and I2 are, or V1 and V2 are. So I don't say I want V1 to be 1 volt. I want this box to give me the voltages and currents that satisfy this condition. It's not a supply. Like, I'm not saying this is 2 volts, this is 1 amp. It says whatever they are, the two currents are equal and the two voltages are equal. Find voltages and currents that satisfy these two conditions. And you will see that it doesn't happen for everything. It happens for certain conditions.
So you don't specify either one?
I don't specify the value.
Okay.
I just specify the equality.
Okay.
And you will see how it corresponds to the equations. You will see that it actually does work. So that's a good question. So anyway, so if I want to get, first let's do the the currents. If I wanted to equate the current, make something that forces two currents to be equal. What is that? We know how to make that, right? It's a current mirror. So I'll start with the current mirror. Can make a PFET current mirror. Two branches, one side is diodes connected to get this bias voltage. Fine. But this doesn't guarantee that these two have any equality, right? I mean, they are whatever they are. So how do I make them to be equal? So now I add a second device, a pair of devices actually, NPETs, like that. Now, if these two are carrying the same current, and they have the same W over L, what can you say about these their VGSs? Forget about the channel length modulation. So they have got the same VGS. But if this voltage is common among them, it means that these two voltages have to be equal. Correct? Now, this of course has a little problem because this is floating in the air. There's nowhere it comes from. So I have to make this something like that. And it has to be on the opposite side of that, otherwise I will have two diodes in series, which basically says this voltage will be determined by the supply. We have supply dependent. But then once I click on the other side, the variations will be absorbed here and there if the supply is changing. So, anyway, so if I start with this, what does it do? It forced these guys, force the currents to be equal, and these guys force these two voltages to be equal. If you ignore the channel length modulation. Now, if channel length modulation is an issue, you make these guys a cascode and these guys cascode. You can make these cascodes. You can do two sets of these and two sets of. This is what I call a floating mirror. You can think of this part. This is the mirror, and this part is what I call the floater or the isolator. This isolates the mirror from the rest of the circuit. Or floater. And this one is the mirror. Now, let's say I have something like this, and let's write the equation. The equations now are pretty much the same equations that I had before. So I have Vt plus delta VGS, which is the VGS of this guy, is forced to be equal to IR. But then Vt, and this delta VGS is basically I divided by I1 and I2 being equal, I call them I, mu n Cox over 2 W over L of this guy. Therefore, I is Vt, the threshold voltage over R, plus 1 over R square root of I over mu n Cox over 2 W over L. Okay, so I got exactly the same equation as before. So if I wanted to play this game, I could say, well, make this is another way of making the same thing, right? I can make this W over L large, then this becomes independent of that. But can you think of a more clever way now that we have this to eliminate this? Not asymptotically by making W over L very large, but systematically. You remember the trick that we started off with? So let's think about the voltages. This voltage is what? This is a Vt plus delta VGS. What is this voltage?
2 VT.
2 VTs plus 2 delta VGS. And therefore this voltage is again Vt plus delta VGS. The problem arises that from the fact that I drop a Vt plus delta VGS across this R. I want it to be what ideally? Ideally I want this to be just Vt. So I want this to be 1 Vt lower. So I need to drop, maybe I can, if I can drop 2 delta VGS, not 1 VT, not delta, 1 delta VGS lower, not 1 VT. So what if I get 2 delta VGS across this guy? Right? If I make this VT plus 2 delta VGS, this voltage drop. This works, right? How can I do that? What do I do to W over L? Make it a quarter, right? So if I make this a quarter, then this term disappears. Because this voltage becomes Vt across R, and therefore my I becomes Vt over R. Systematic. So I can make it then, if you want to make a copy of it, of course you take this, and this whole thing is one instance of, this is not the best one, but this whole thing is the current source, the reference current source is an example of how you make that reference current source. And they said, okay, we'll talk about it later and tell you how we do this. This is one example. This whole box is that. And you'll see that we will make it more sophisticated boxes as we go. So, anyway. Now, is this good? Well, it has this way it has less dependence on, it doesn't show a direct dependence on the supply. Of course, if you have, it depends on the channel length modulation. If you take channel length modulation into account, then you have some dependence on supply. It has significantly been reduced. You can even reduce it more by making them Cascode. So you took care of the supply dependence, the first order, but how about other things like temperature and process? Well, we clearly have process dependence because both VT and R depend on process. Because what determines the threshold voltage? The implant charge in the channel that can vary. That can vary from one transistor to the next on the same wafer or die. And it can vary more from one wafer to another. And it can vary even more from one lot to another. One time you make one set of chips, and the next time, like 3 weeks later, you make another set of chips, and they will be more different. Same thing with R. How do you make resistors? The resistors are made out of doped pieces of silicon, or silicon dioxide, or silicon polysilicon, right? Or other materials. No matter what, I mean, they depend on the doping levels and the materials and all those things. So they definitely have process variation. How about temperature variations? Well, the resistors generally have temperature dependence, right? Typical resistors have positive temperature coefficient. You can make resistors that are negative temperature coefficient, but generally the standard ones that you make have a positive temperature coefficient. Now, VT, the threshold voltage, has a negative temperature coefficient, and this is something that you didn't know, so I'll tell you. You can do the physics and all those things, but you can see that it has a negative temperature coefficient. It's approximately around -2 millivolts per Kelvin. So that's how much the threshold voltage changes per degrees, basically. So it changes by -2 millivolts per degree, the threshold voltage. So if you have 10 degrees change, approximately it changes about 20 millivolts. This is a ballpark number, 2.5. So is this a good thing or a bad thing that one has a negative temperature coefficient and the other one has a positive temperature coefficient? It's a bad thing because it's a ratio, right? As the temperature increases, this becomes smaller, this becomes larger, this I is quite temperature dependent. So,
But it could be a good thing too.
well, it depends on what you're trying to do. I mean. But if I'm trying to make something that's stable with temperature, doesn't change with temperature, this is not that. It also has process variation. So making it reference with VT is one way to do things. If you want to make something that is just temperature, supply independent, you could do it. And some people do it still for some designs which are not very temperature dependent or sensitive to temperature. Can you think of one kind of application that has almost no temperature dependence, or you don't care about temperature stability? You know that you're working in an environment that's relatively more or less stable.
Outer space.
Outer space, well, no, that's actually the opposite kind of, right? Because if you're exposed to sun, then you can quickly heat up and then it has more to do with inner space.
Refrigerator.
No, refrigerator. Implantable devices. Because your body, I mean, is more or less within a couple of degrees range. If you're out of that range, then you have a bigger problem than the circuit not working, right? If you've got like a 25 degrees C inside your body, then the circuit's not working perfectly is the least of it wrong. Anyway, so there are examples where you may not worry too much about it because the temperature is controlled by some other mechanism. Sometimes you're so sensitive to variations that you do everything, but still you don't get the stability that you need. So you make these things that are these references, for instance, frequency references that are called the oven control crystal. So they make this crystal, they make it as temperature independent as they can, and then still they want to make it so stable they put it in a temperature controlled oven. They make a chamber which is basically heated to a fixed temperature and it's kept there through a feedback loop. So depending on what you're trying to do, you may go through a great effort to make things stable. Anyhow, so that's basically one way to do one kind of reference. So what else is there? If you yes.
Can I ask a quick question? As far as the magnitude of currents you can get from a configuration like this, aren't we limited because VT is what, a couple tens of volts? I mean, if we decrease R too much, then yes, technically you can go high currents, or you have to have a huge R for very low currents. I mean, how?
Well, you can scale it up and down here, right?
Right.
You make one reference branch, but you can scale it up and down. You can basically make it 10 times larger by making this W 10 times larger or smaller. And since it's the ratio of two W's, that doesn't affect your general behavior, because if you're thinking about the physical lengths would expand and shrink with temperature the same way. So the ratios are fine. So, and one of the tricks, actually this goes back to something that's very important. Eventually, the key trick to making things independent of everything is trying to make it defined in terms of ratios. If you make things defined in terms of ratios of parameters of the same kind, ratio of resistors, for instance, two resistors that are made of the same material and are in close proximity of each other, therefore they are at the same temperature. And if you make them out of the same material, they will have the same temperature coefficients. It doesn't matter, right? If you have like a ratio of a 5 kilo ohm to 1 kilo ohm resistor that's made out of something, remains the same with temperature. Because temperature increases both of them by the same percentage, so the ratio doesn't change. So you will see that eventually the things that are independent of most things are built on ratios of things. That's the trick. That's the ultimate trick. But the question is to get there, you have to know how to make things that are defined only in terms of ratios. So, but before we get there, so VT was one of the things that we had in the process. What else do we have? This was one of the voltages that we had there, right? So you identified it. Is there something else that's more or less constant? We say, well, some of our analysis, well, we can say ballpark, this is about so many volts or something like that, when we did like biasing analysis, for instance. VBE, for instance, right? You said VBE of the transistor, because it had a logarithmic dependent on the IC, for a given range of currents, it doesn't change that much. So what if we had a VBE, if I wanted to make a VBE reference? How could I make a VBE reference? Now you should be able to tell me, because I've taught you this floating mirror trick. So how would you change this if you were to make a VBE reference instead of a VT reference?
Change this to
To bipolar, to VJT, right? This is the beauty of this thing. So what you do, maybe you can go here, and I'm going to redo it to make it cleaner. And you can make a floating mirror in bipolar and MOSFET, so it doesn't matter. But a more common MOSFET implementation. The only key to it is that they can't be diodes connected on the same side. The floater and mirror should be, or the isolator and the mirror should be diodes connected on the opposite side. Okay, so I'm going to make a VBE here. So I need some sort of a diode or diode connected device. But I'm in a MOS process. Let's say I'm in a pure CMOS process. You could have a BiCMOS process where you get both bipolars and MOSFETs. But if I'm in a pure MOS process, can I get a bipolar? Can I get a VBE?
Yeah, junction.
I have junctions still, right? I mean, all I need is really a diode. I need the PN junction. But if I want to get a VBE, even if it's like a transistor kind of VBE, I remember I have a P well in a most basic vanilla process. So if you can get it in the most basic vanilla process, you can get it in anything, essentially.
What process?
Vanilla. Vanilla, I meant like a very standard, right? The most standard flavor of an ice cream, I guess, is vanilla, right? When I say vanilla process, I mean like a very standard, nothing fancy, no strawberries, no chocolates, no chocolate chips, no gummy bears. So very standard process. So then you have an N well. Oh, sorry, this is a P sub, sorry, not P substrate. It's an N well, and then this is how you make your P FETs, right? And then you have N pluses in there, P pluses, sorry, P plus. So you have a P plus NP, which is a good bipolar transistor, a good PNP because it's a P plus, you can make a contact here using your N plus to this, so this becomes your base. But the only problem with this one is that its collector is connected to ground. So be it. It's called a substrate transistor, right? So it's a bipolar transistor whose collector is guaranteed to be connected to ground, so you can't connect it anywhere else. But you still have access to base, and what do we do? Just like you connect the base to ground, like that. So you get a VBE. One way of doing it. So even if you didn't have bipolars explicitly, you can use the structures that you have to make a bipolar BJT. So now you have a VBE, and this is R, so I already know what this is, right? So this voltage is the same as that voltage, this current is the same as that current, so I know the VBE is going to appear across here, is going to be IR, and therefore I is going to be VBE over R. Not too difficult. So this current will be proportional to VBE, inversely proportional to R. Now, what do you think the temperature coefficient, so it's like more or less constant, but in terms of supply, but the temperature coefficients of VBE, what do you think it is? Positive or negative? Negative. Okay. So how many people think positive, how many people think negative? Raise your hand if you think it's positive. Raise your hand if you think it's negative. We have one person for positive, one person for negative, and the rest of you for 0. I can't see any other options. No. Okay, well, it's a trick question. So let me write it in a way to trick you first. So VBE is VT ln of I over IS, right? IC over IS. This is the exponential behavior of the transistor, right? And what is VT? KT over Q is TB temperature, ln of IC over IS. So if you look at it this way, you would think that it's a positive temperature coefficient. When you measure it, you see it's negative temperature coefficient. It's approximately the same as the V threshold, approximately minus 2 millivolts per degree C or Kelvin. So, why? Well, IS has such strong dependence on temperature that even through the log, it still overwhelms this T. And this is something you're going to see. That's why I say it's a trick question. Okay. I'm going to tell you what the dependence is. So what is IS? IS, actually you can derive an expression for IS when you do the transistor analysis. It's proportional to the area of the base, of the emitter basically. Ni squared, which is the intrinsic concentration of electrons and holes. D, and there's a Q, and then there's a D, which is the diffusion constant, divided by W, which is the width of the base region, and one more thing down here. Oh, Na, the doping concentration of the base. So there are a bunch of different things. The area doesn't depend on temperature that much. I mean, there's a thermal expansion, but that's nothing compared to the rest of that. So Ni squared of the intrinsic concentration of electrons and holes, the charge carriers. That has a dependence that's like this. It has some constant C times T to the 3 to the third, and an exponential dependence on the Vg0, which is the band gap of the semiconductor. So if you remember the energy band diagrams, the difference between the conduction band and the valence band, this is the band gap. Well, it's Q times this is the band gap energy, and this is the band gap voltage. For silicon, it's about 1.1 volt. For different semiconductors. And it makes sense that there would be an exponential dependence, because you remember this is the tail of this thing can be approximated as a volt per distribution. It's a very Dirac distribution. So it's an exponential dependence, inverse exponential dependence. The larger you make the band gap, the smaller you will have, the smaller number of free carriers, because these are the free carriers, the ones that have enough energy to make and there's a t to the 3 there. So, and then there's the Einstein relation for diffusion. D over mu is kT over Q, and it rhymes. That's the way to remember it. So you can apply this, and mu, so basically then you relate this to mu. And mu is basically another constant, well, it's a d prime, t to the n, minus n. And at room temperature, n is approximately 3/2. What happens is that mobility changes the temperature like this. So the mobility first goes up and comes down. So at very low temperatures, because of the impurity scattering, you have a slope of 3/2. It's exponent of 3/2. And then at room temperature, which is down here, you have an exponent of minus 3/2. So you have minus n per n is 3/2. So you plug all of these things in, you get some constants. Ni gives you a T3, right? T to the third.
Is it squared?
I'm sorry?
Is that ni squared or just ni?
Ni squared. Yeah, Ni squared. T to the third, and then you get, from D, you get a kT over mu, Q cancel, so you get a 4, because of that T gives you a 4. You get a T to the minus n, so it's from there, you get and then what do you get? W and n are independent of temperature, and then you get the exponential. Times some constant, E. This is Is. As far as the temperature dependent elements are concerned. So I've taken all the temperature independent things out and lumped them into this constant E. And then, so let's plug it into the VBE expression and see what we get. VBE is VT, right? ln of IC minus VT ln of IS. And, okay, what does it look like? So VT ln of IC minus VT ln of E minus VT ln of, and the exponent comes out, so we get VT times 4 minus n ln of T, so this term, minus, and there's a minus sign here, so it becomes plus, so it's ln of an exponential. You get the argument, minus sign cancels, a VT cancels, so it's plus VG0. So you see that your band gap, your VBE, is a band gap voltage of the semiconductor. It's a property of the semiconductor and quite independent of temperature, actually. The energy band diagram between this is determined by quantum mechanics, essentially, right? And the spacing of the atoms in the lattice and things of that sort. Minus all the terms that depend on temperature, right? You can say VT times ln of E plus 4 minus n natural log of T, and then plus VT ln of the IC, the collector current. So that's your VBE. Now look at it. Does it have a positive or negative temperature coefficient? This is a constant. It's a minus sign in front of this term. Actually, you can take this here. Yeah, that's fine.
It depends on the temperature.
It depends. Well, what do you mean it depends on the temperature?
Curve.
I mean the curve,
No, if this current is not huge, this current has to be huge to overwhelm this. This current has to be like hundreds of amps overwhelm that. But other than that, all the remaining terms have a negative coefficient. And that's why it's basically inversely proportional. VBE is inversely proportional to temperature. And this kind of reference, it's called CTAT, or complementary to absolute temperature. So CTAT stands for complementary to absolute temperature. So it seems that we could get another source, but it also has the same problem. What do we really need if we want to get less temperature dependence? has a positive temperature coefficient. What is that voltage? VT, right? KT over Q. If I somehow could get KT over Q out, then that gives me a positive temperature coefficient. Right? Because KT over Q by itself will have a positive temperature coefficient. Because I doubt that either K or Q will have temperature coefficients. Right? They're constants of physics. So, how do we make that? Where do you get a VT? Where do you see a VT? Not the actual voltage, I mean, which expressions do you see VT in? The collector current thing, or like VBE, the expression that we have, right? So VBE itself had a KT over Q. It's VT IC over IS. The problem was this IS. That messed it up. So somehow I have to eliminate IS. How do I eliminate IS out of this? How can I get rid of IS?
Ratio.
Subtract.
Correct. Ratios of the. Okay, so you're both saying the right thing. Ratios of the arguments. If I can get this the argument of the log to divide by another thing that has an IS in it, then it would go away. But to get the arguments of the logs to divide, you need to subtract. So you need to subtract two VBEs. What if I subtract two VBEs? So let's say call this VBE 1 and then subtract the VBE 2. KT over Q ln of IC over, let's say transistor that's n times larger. N of x. Or n transistors in parallel. What if I subtract these two? What is VBE 1 minus VBE 2? So it's natural log, this log minus that log, which is basically the ratio of those two arguments. IC over IS divided by IC over NIS. And if I force them to have the same current, that term also cancels. So everything cancels here. I'm left with KT over Q, natural log of N, which is the ratio of the sizes of the transistors. It's a good thing, ratio of the sizes, right? Or you can make it the numbers. So you can have one transistor and then n transistors in parallel carrying the same current. So I need to subtract 2 VBE. And then if I can subtract 2 VBE, then I'm good, right? Because I've eliminated the IS. How do I subtract 2 VBEs? And make a current that depends on their difference. Would this work? Let me just so try something. Well, so this is one VBE. This is the other VBE. This is the resistor. Would this work? The current from this resistor should be the difference of the VBEs, right? Yes or no? This is VBE 1. This is VBE 2. This is R. Do you agree that the current through R is the difference between VBE 1 and VBE 2? What is the solution? That what I said is correct, but unfortunately it's 0. It's the difference of 0 and 0 if I do it this way.
But you already have the structure.
I know. Because people do this, that this is the reason I do it, right? People think this way. I'm just trying to tell you what is wrong with in that solution. There's nothing fundamentally wrong. You do get the difference of 2 VBEs, but you get the difference of 2 zeros, which is still a 0. So you need to have a non-zero current for this to be useful. So how do you make non-zero current? Then use one of those floating mirrors. Here. So this is one of those floating mirrors. I can draw it, or you can just basically abstract it. This could be a good name for like a drawn floating mirror for a book. No, the floating mirror. Okay. Anyway, so if I do this now, what do I do? I force these two currents to be the same. So this is I and this is I. And basically, this voltage is the same as that. So this voltage is VBE1. And this voltage is VBE2. And this difference is dropping across off. And then I can branch out of this and copy it, like we did before, and get that voltage out. So if I do this, this is what we call this gives you a KT over Q. What is the current then? The current is going to be, I is going to be, the difference of the VB is divided by R. So it's going to be KT over Q R, natural log of N. So if I were to, not to abstract it out, show you the details, this is one way of doing it. The current is that. This is called the PTAT, proportional to absolute temperature. It's a current that grows with temperature. And in terms of temperature independence, it's probably better because you have two things, the ratio of two things that are both proportional to temperature. Or like increase with temperature. They have both positive temperature coefficients. Okay, so that's for that, but now what? Is this good enough? Now, let me ask you this question. If I wanted to generate a voltage that's independent of temperature, voltage, how would I do it? Can you think of a way? Do you see anything in this whole process of this whole discussion that was not dependent on temperature? The Bandgap voltage, right? The VG0. It's a property of the semiconductor. So how can I get that band gap? You see, I have a bunch of things that are dependent on VT. If I add enough VT to a VBE, remember VBE? What is VBE? If you look at the VBE, you see VBE is the band gap voltage plus the VT. So if I want to get the band gap, I have to take the VBE and add it to something proportional to VT. So in other words, if I have a PTAT and I already had a CTAT, if I add them with the right ratio, I should be able to get something that's more or less constant, which would be the band gap. So what do I do? How do I add this? So I have the current that's proportional, so this current I is VT, the KT over Q, over R, natural log of N. What do I do with this? How do I add it to a VBE? This is a current. I have to convert it to a voltage again. Right? A resistor. R2, let's go with R1. And then what do I do? Add it to a VBE. Let's put the VBE here. So this voltage across this guy so this voltage is going to be R2 over R1, L at natural log of N times KT over Q, or VT. And this voltage is a VBE. So this voltage, if you think about it, is the sum of the two. Right? So, and the good thing about driving the VBE with that current is that, look what happened. So it's basically, you get this term and subtract it from that term. Now you can see that there are other terms in there, but they're weak dependence on temperature. It's a log dependence. So this doesn't exactly cancel it. But it reduces the sensitivity substantially because these are not straight lines exactly. So what happens is that you get curves that are like this with temperature. But by controlling the ratio of these R and the VBEs, you can actually make this optimum point where the derivative is 0 and they happen at different places. you know you're going to make a temperature reference that's working around room temperature, you make this happen at room temperature. If you were to do it at like lower temperature, you can make this like that or that, but you get the voltage close. The thing is that the voltage you get is close to the band gap essentially, the range of the band gap. It's like 1.1 volts. You can actually buy these things. They're like very cheap now. And if you want to make it voltage, that's fixed. Yes.
What's the advantage of adding another branch to produce that voltage while we can, I guess we can produce it in the branch limiter, right?
The problem and the advantage, why don't you take it from there? Yeah. You can't take it from there.
But you have to.
The problem is that you have to buffer it, right? Because if you start drawing current out of it, then you mess things up.
Yes, but we have to do that even when we want to take the output from the other branch.
Correct, but it's basically separated from your core because this messes up the general difference behavior. This is somewhere outside. You need to buffer it, but here you're a lot more sensitive to variation. You can take it from there. Actually, another way of making the band gap, which is probably even more common, is that the problem with this is that a lot of times to make these things very constant is that you need to make these cascode and you need to make these cascode, and then you lose a lot of headroom. Now, with the reference, it may be okay still, because you know the reference voltage doesn't change that much. That's the whole point of a reference. So you know exactly what range the voltage is. It's not an amplifier whose voltage needs to change over a broad range. But nonetheless, there's another way of doing this, which is like this. So you take two VBEs, and two resistors, connected transistors, and then you basically take this voltage. So let's call this R1, R2, and R3. And then I want to force these two voltages to be equal. This is another way of achieving that thing, right? Forcing these two being equal. But it doesn't necessarily force the current to be equal in this case. So these are both the same size, by the way. In this case. So if I wanted to force these two voltages to be equal, what do? How can you do that? We know of something. We learn asymptotic equality principle. See, that's where that is useful in design. You want two things to be equal. You want to force them to be equal without driving current directly into them. You make them, you apply them to an amplifier with a gain of A, and you drive this voltage. Now you just have to pick the right polarity for the feedback to be negative feedback. So if this goes up, let's assume that this is positive negative. This goes up, this pushes this up, this goes further up. So this is wrong, so it has to be the other way around. If this goes up, this goes down, this pushes this down. So using feedback, if I have a large enough gain, and an amplifier whose input doesn't draw a lot of current, which is basic op-amp, it can be even a single stage op-amp, one of those like currents differential to single-ended converters. If you have something like that, I can basically use this. And what happens is that it forces these two voltages to be equal. So if these two voltages are equal, the same set of equations kind of apply. So what do I have? This voltage is the same. These two voltages are equal. So it means that this current, this voltage has to be the same as that voltage, first of all. Right? So it means that, let's call this I1, or I2 I guess, and I1. So what that means is that I1 R1 has to be equal to I2 R2. That's one thing I know. The other thing I know is that these two voltages are equal. So this VBE minus that VBE is going to be the voltage drop across this guy. So you can say this voltage is, or let's calculate the current. So I2 is going to be VBE of this guy, VBE1 minus VBE2, VBE of this guy, divided by R3, it's going to give me I2. the ratio. That's my I2. So I2, the current is a PTAT, is a VT current. But now you have that current going through this resistor added to this resistor. Or the same here, where you can say that current, the same current, this current is proportional, is added to this. So this voltage is a V band gap. You can make it a V band gap if you pick the right ratios of R's and R's to eliminate that. So it's basically this plus that voltage is this voltage. Right? This is the voltage out here. This is the voltage out there. So that's the band gap voltage. So that's another way of making a band gap. Now, one last thing on this. Sorry. Now, let's say you want to make an amplifier whose gain is independent of temperature. How would you bias it? Let's say it's a bipolar amplifier. So BJT. Let's say you're making a differential amplifier. You could bias it with the band gap current source in such a way that its current is constant. You could bias it with a constant current. So I'm making a differential amplifier. Let's say something similar. With resistive loads. And you want to bias it somehow, so the differential gain is independent of temperature and supply and process. How would you bias it? Well, you have to find out what the gain is first. We've determined what's the gain of this thing, what's the voltage gain from differential input to differential output. GMRC, right? GM, well, depends on the polarity, how you choose to define the polarity, but yeah, negative positive. So AB is that. So I want to make this independent of temperature. This doesn't look independent of temperature, right? Because what is GM, by the way, for bipolar transistor? IC. So let's call this I bias. So this is IC over VT RC, and therefore, if IC is like half of I bias, right? So it's I bias divided by 2 VT RC. It's balanced. Okay? So how do I make this independent of temperature? For supply. What kind of we've introduced several types of sources, right? We saw threshold voltage, we saw PTAT, which is like proportional to temperature, like a VT reference. We saw VBE reference, which is CTAT, complementary. We saw a constant reference, we can make something that's more or less constant, we can add them in any ratio they want. So basically, once you have a PTAT and CTAT, you can create any slope you want. By combining them with different ratios, by changing the values of R1 and R2, you can add them with different coefficients, so you can make any slope you want. Positive, negative, constant. So essentially, once you have those two, you can do anything. Right? So, how would you bias it?
You have to use PTAT current for the bias.
So first of all, yeah, you want something that is increases with voltage or with temperature or decreases with temperature? Increases, because VT is in the denominator, right? So you want I bias to be proportional to VT, kind of. So, how do we do that? Help me out. So I need to make a VT reference, a PTAT.
Are you assuming that RC doesn't change with temperature?
Well, let's see. Let's find out. We'll get to that. It's a good question. One thing at a time. I can make that about 4, so it doesn't matter. I can make that. So let's assume it's a bisequence process. Doesn't matter. I mean, these could be combined. I could just turn them into bipolar. So if I have that, this is R. Let's call this R1. We know what this reference current is, right? What is this reference branch current? We've done this before. It's VT over R1 times natural log of N. So this has to be 1x. No. This has to be N, actually. This has to be 1. How do I know which one is N, which one
1 minus 16.
Yeah, so this voltage has to be greater than that voltage, right? For voltage to be greater than that, then IS has to be smaller. Because it's in the denominator. The VBE, right? VBE is natural log of IC over IS. So I want this VBE to be greater than this VBE, therefore this IS has to be smaller than this IS. VBE, VT natural log of IC over IS. Okay, so I take this, so this is the PTAT, and then I need to bias this somehow with that, so I can use this guy, bring it here, and do that. So what's my gain now, if I use this reference? Let's say these are ratios of 1, you could change it later if you wanted to change those ratios. Okay, so this current, this is the current, I bias. So if I plug that into here, what do I get? I get VT over R1 divided by 2VT times RC. Therefore, this is RC over 2R1. So that's my gain. So it's independent of supply. Now, if I wanted to make it independent of processing temperature, what do I need to do about RC and R1? You make them out of the same kind of material. So you don't use a polyresistor for one and a diffusion resistance for the other. Use the same material, you try to place them as close as possible to each other. So they are at the same temperature, as similar as possible. And therefore you have a ratio of these two things. So if they have the same temperature coefficient, this becomes independent of temperature. And independent of that temperature coefficient, which is the process dependent thing. So it's really determined by the ratio of two things. Does this make sense? Okay. Any questions? So what we saw today, we basically learned how to make that little reference current, right? And we see that depending on what you're using it for, you may use a different one. But there are different kinds that we can use. And to use it as a reference. We saw that you never eliminate anything, you just basically reduce the dependence on different parameters, but you can reduce it quite a bit. And we saw these techniques, so these are very useful techniques in biasing things independent of supply and temperature. Alright, if there are no questions, let's take a quick break.